it has.
All right, so first question we're going to look at gives us a polynomial, and they want us to find all real zeros. So because it's a cubic, we can't jump right to quadratic formula. We have to first take the cubic down to a quadratic, and we have to do that by finding a root. What's the name of the formula we use to try to find roots that you can write as fractions? Yep.
P over Q.
Yeah, what's the name of that?
Rational root theorem?
Yeah, rational root theorem. So when we use rational root theorem, we list the p's and the q's. P's are all the factors of the constant, which in this case is 9. So what are all my factors of 9? Yeah.
Plus minus 1, plus minus 3, plus minus 9.
1, 3, and 9. Okay, and what about all the factors of q?
Plus minus 1, plus minus 2.
Plus minus 1, plus minus 2. So now we're going to write down all the different p over q options we could have. So we could have 1, 1/2. We could have 3, 3/2. And we could have 9 and 9/2. Now that's a lot of different options. That's 12 different options we would have to try synthetic division with. So how can we narrow that list down? Yes?
Use the graph.
Yeah, let's use the graph. Okay, so let's type those in and see what we've got. So 2x cubed minus x squared minus 9x plus 9. I know I only have to look between negative 9 and 9. Those are the biggest and smallest. Okay. So now looking at that picture, are there any numbers in that list that looks like it shows where that graph crosses? Yeah?
3/2.
I would say 3/2. That's the only one that looks close, like 9 and negative 9. Those aren't 3/2. No. I mean, this is a little over negative 2, but I don't have any numbers here that are close to negative 2. I got negative 1.5, and that's about it. So I would say 3/2. So what we'll do is go to the table. Let's check 3/2. Perfect. 3/2 is a root. So now we have to divide through synthetically so we can turn the cubic into a quadratic. So let's put 3/2 on the outside. And what are going to be my numbers on the inside for the synthetic division? Yeah, Travis?
2, -1, -9, 9.
Negative 9, 9. Okay, let's do our synthetic division and see what we get. So bring down the 2. 3/2 times 2 gives me how much? 3. I'm going to add negative 1 plus 3 gives me 2. Well, that's nice. Same number again. 2 times 3/2, we just did that, is 3. Negative 9 plus 3 gives me
Negative 6.
-6. Negative 6 times 3/2, that's negative 18 over 2. What's negative 18 over 2?
Negative 9.
Negative 9, and as we expected, remainder of 0. So now let's put 3/2 in our list of roots. Is 3/2 rational or irrational? What is it?
Rational.
Yeah, that's rational. Now, what do we look at after we do the division to get the other 2 answers? Because we know there's 2 more answers to this problem. Yep.
You put that into a polynomial and then factor it.
So we could try to factor this. Look at the quotient. The problem is that's not, I can look at it and I can tell it's not factorable. So how are we going to solve that when we set it equal to 0?
Quadratic formula.
Right, we're going to have to use quadratic formula. So now you're setting what's left, which is the quotient, equal to 0. Okay, so we'll fill in quadratic formula. And that's going to give us the remaining two answers. So negative b plus or minus square root of b squared minus 4 times a times c, all divided by 2a. We're subtracting a negative, so that becomes a positive. And we have the square root of, what's 4 times 2 times 6? 48 plus 4 is 52. And I think we can reduce the square root of 52. Yeah, 4 times something is 52. 4 times how much? 13. Yep. So we can write it as 2 square roots of 13. So negative 2 plus or minus 2 root 13 over 4. And now that we did that, what's everything divisible by? 2. So divide everything by 2. 2, 1, 1. So your final answer is negative 1 plus or minus root 13 over 2. These are the other two roots. Let's just go like this. And are those roots rational or irrational? Those are irrational. And that's the only way we can get those. We can't get those by graphing them and just calculating a 0, because that's going to give us a decimal. Right? So if I ask for the exact answer, you pretty much have to go through those steps just like that. Any questions on using the rational root theorem, synthetic division, or the graphing calculator, or quadratic formula? It's like 4 questions right there, all in one.
Wait, can you say that again? What did that question cover?
So that question covered using the rational root theorem,
Okay.
using the graphing calculator to eliminate roots that don't make sense, using synthetic division, and using the quadratic formula.
Thank you.
You're welcome. All right, so this one, they want us to determine if 2 is a root. And we don't want to do it by plugging in 2, because they may ask us for the quotient as well. So while plugging in 2 would tell you if it's a root, it wouldn't give you the quotient if I ask you for that on the test. Okay, so what is equivalent to proving 2 is a root? Something else I can do, but it means the same thing as 2 is a root. Yeah?
Saying the factor is x minus 2.
Right. Instead of proving that 2 is a root, let's prove x minus 2 is a factor. So if we can show that it's a factor, then it means 2 is a root. How do I prove that x minus 2 is a factor? Yeah?
You do out division and then factor it.
Do out the division, and then what happens after the division? I just do the division and then I'm done. I just got to look at my result and figure something out. Yeah.
If the remainder is 0.
Right, if the remainder comes out to 0. So do we want to do this with long or synthetic? You can do it either way. Savannah, you get to pick.
You said that.
Synthetic, okay. So what number would go on the outside? Or Layla, what number would go on the outside? So we're proving that this is a factor.
So 2.
So the number after the minus sign is a 2. And Alexis, what about my numbers on my inside?
2, -3, 4, and -9.
Yep, no numbers missing, so we're good there. So we'll do the synthetic division, but the point of this is to look at the remainder when we're done and then figure out if 2 is a root. Okay, so bring down the 2, add those up, we get 1, 2, 6, 2 times 6 is 12, 12 minus 7 gives me 5. Okay, what is my remainder there? Yep, remainder is 5. So is x minus 2 a factor? Nope. So is 2 a root? No. Okay. Any question on that one? Okay, so next question we're going to look at. They've given us 3 numbers that they want as roots, and we have to work backwards and figure out the function that would have those roots. Okay, the first step is if they give us the roots, we've got to convert all those roots back into something that's equivalent. So what do we know if 12 is a root, or if 12 is a 0? What do we know? Like, where would that 12 have come from? Yep.
X minus 12.
Right, it would have come from a factor that was x minus 12. How about if 3 is a root? Yep.
X minus 3.
It would have come from this factor. And what if 1 is a root?
X minus 1.
X minus 1. So now just multiply that out. So we're going to get x squared. We're going to get minus 3x minus 12x, which gives us negative 15x. And negative 12 times negative 3 gives me 36. Okay, a little bit of a bigger number there, but I guess that's because we had to deal with a 12. But that's okay. So now we're going to do it one more time. That's all right. We have a 1 here, so 1's a good number because it's not going to be hard to multiply. So what's x times x squared?
X cubed.
X cubed, and x times negative 15x, and x times 36.
36x.
36x, and now multiply all of those by negative 1. So minus x squared, plus 15x, minus 36. Okay, combine like terms. We get negative.
25.
What's that? What? You don't like the number 12 now?
No, I was saying it's not even that bad. I could have said number 25.
Yeah, no, it's not that bad. Not really. If somebody had said like 9 is a root, then we got to do 9 times 36. That would have been a little bigger, but still, we have calculators, so we'd be okay. So we got x cubed minus 15x squared minus 1x squared. That's minus 16 x squared. How about my x's? What do I get when I combine those? (51x). And the last thing is my constant, and there's nothing with that. Okay. So that should be a polynomial that goes through those 3 numbers. How could we check that that's right? Yeah, we'll just graph it and then see if it goes through 12, 3, and 1. Okay, we can't use the standard window because we got to look for the number 12. But that's okay. So we got x cubed minus 16x squared plus 51x. So that's probably going to go way off the screen, but we don't care how high it goes. I just need to see the 12. What was it? 12, 3, and 1. So let's put our x max at like 15. Hopefully we have 12, 3, and 1. Well, there's 1. There's 3. 12 should be perfect. Okay, so that works. Okay, so the next one, we're looking at 3 different graphs, and they want to know whether they are continuous or discontinuous. Okay, how about the first one? Is that continuous or discontinuous?
Continuous.
That's continuous, because we can draw that without ever lifting our pencil, and the domain there is all real numbers. There's no breaks, there's no gaps, there's no holes in the graph. It is continuous. How about the second one? Continuous or discontinuous?
Discontinuous.
That's discontinuous, right? The domain is still all real numbers. Right? Every x value is covered, but the problem is to get from this part of the graph to that part, you jump. Okay, so that's discontinuous. Discontinuous. And how about this last one? Continuous or discontinuous? Yep.
Discontinuous.
That's also discontinuous, right? Different reason. This has like a break, or like you have to jump. This has a vertical asymptote, which we haven't learned that name yet, but we will later on. Okay, so that is a vertical asymptote. So literally that's just looking at a picture and determining if it's continuous or discontinuous. That's it. All right, so let's take a look at this graph and identify the points of discontinuity. So that would be anywhere that you have to pick up your pencil as you travel along the graph. Okay. Does anybody, and you gave me the x value, that's how you describe it. Are there any points there that are discontinuous? Yeah?
2 to 3.
So you just have to give me a single number.
Oh,
2, yes. There is a discontinuity at 2 because you have to lift at 2 and then put it back down. So x equals 2. Where else are there discontinuities? Yep. -3, yep. There's a hole in the graph right there. So you'd have to trace along it, lift up, put back down. Okay. Where else do we have discontinuities?
-4.
4, yep, we have a vertical asymptote. So that's splitting that into 2 pieces. And where else do we have a discontinuity? Yep.
-7.
Yep, -7. So when you're on this part of the graph, to then get to this part, you'd have to lift the pencil, put it back down. Yep. Those are all the points of discontinuity in that picture. 1, 2, 3, 4 of them. Okay. Any questions on that? All right, so let's first take a look at this and find the end behavior model. So the end behavior model is a single term up there that predicts what this graph would look like if you zoom out. Which term up there would be the EBM? Yeah?
The 4x plus 6.
Why not the first term?
Because you do the one with the, I thought you did the one with the greatest exponent.
Right, you always look at the one with the highest exponent, which if you write it correctly should be the first term, but in this one it's not. So -4x to the 6th is the EBM. Now I want to know the actual end behavior. For that, you're going to look at the model, and there's 2 things we have to look at, and those together are going to tell us the directions this one's going to go. Anybody know the direction that the ends of this polynomial are going to be facing? Yep.
Down, down.
Down, down. Okay. Even exponent means they're going to go the same way. Odd exponent would mean you have one of each. Okay, but this is even, so they go the same way. And if it's negative, they both go down. If it was positive, they would have both been up. Okay, this one's negative. So down and down. Now let's take this one and let's write it with limit notation. If I'm going to write that in limit notation, what do you think the first thing is I have to write down? Yeah?
Like limit f of x.
Yep, the limit of f of x
And then
as what? As what?
x or negative infinity.
Okay, we're describing the one on the
Oh, on
right.
the right, so it's regular infinity.
Right. This describes what's happening on the right side of the function, and the right side of the function is as you head to infinity. So what would be the answer to that?
Negative infinity.
Yep, perfect. That's the limit way to describe the end behavior on the right. What would you have to modify here to make it the end behavior on the left? Yep.
Making it the bottom x, the arrows make it negative infinity versus
Yeah.
positive infinity.
If you put a negative right there, that means what's happening to y as you head to the left. This means what's happening to y as you head to the right. And they're both down. Okay, they're both negative infinities on this side. Okay. Any question on describing the end behavior model versus the end behavior itself? All right, so the last one we'll take a look at is finding minimums and maximums in a polynomial. What's the EBM of this one? Yeah?
Up, down.
What's the actual EBM, the model itself? Yep,
Oh,
3x cubed.
3x cubed, and that tells you that the behavior is going to be what?
up, down.
Which side is up? It's not critical to this question, but we do need to know for the test which one is which on other questions. Down, up, yeah. Okay. So it's down on the left, it's up on the right. And what kind of function is that? Yeah, it's continuous because it's a polynomial, and all polynomials are continuous. So it's a continuous function that goes down on one side and up on the other. So what does that tell you about the range? Yeah.
It's infinity to negative infinity.
Right. The range is all real numbers. So for that, we don't even need the calculator. For the mins and maxes, we do. Okay. So first step would be to type that in, which we already have. We'll graph it. Okay, we've got our window. Now we have to find the mins and maxes. How many local extrema does that function have? Yep. Two. Okay, there's one minimum and there's one maximum. It is possible that I give you a graph that has no local extrema. What kind of polynomial wouldn't have any local extrema? Guaranteed. It's possible I could draw a cubic that doesn't, and I had one before I put this one up. But there are certain ones that would never have extrema.
Linear.
Yeah, anything that's linear would never have local extrema, because to have one, your slope needs to change direction. And with linear, slope never changes. Okay, so let's do the minimum. How do I calculate the minimum on the left? Yep. Yep, second trace, and then minimum. So that's all you have to remember. Then you put in your left, your right, and your guess. And you have a minimum at negative 1.31. And maximum is going to be the same, but don't assume that it's symmetric. Like if you have negative 1.31, that you have positive 1.31. No. Okay, just find the maximum and write down what you know. So maximum. Go to the left. Go to the right. And do your guess. And the maximum is at 0.42. Now, what kinds of minimums and maximums are those? They're not the highest minimum. It's not like the highest value it ever hits, because this graph goes a lot higher than that y value right there. But we call that a local. Yeah, that's a local maximum and a local minimum. Okay. Now, let's look at the maximum. If I asked you something specific, like what is the maximum, what would you say the local maximum is? It's a single number. Yeah.
0.4.
No, that's not what the maximum is. Yeah.
7.1.
Yeah, the 7.17. That's the highest that it goes in that area is the y value. When that occurs is at 0.42. Okay. So the x is where the maximum occurs. The y is what the actual maximum is.
Is that the same for the minimum?
Same with the minimum, yep. So the minimum here is at negative 0.67, and it occurs when x is negative 1.3. So there's an important difference between what it is and when it occurs. Any question on that difference?